Hello and welcome to my new lecture. Today's lecture is about heat transfer mechanisms. This is topic 18.12 of the Halliday Resnick Walker book Fundamentals of Physics. In this lecture I am going to discuss different heat transfer mechanisms like conduction, convection and thermal radiation one by one. In our previous discussions we have discussed the transfer of heat energy between its system and its environment, but we haven't still discussed what are the types of different heat transfers. So these are different types: conduction, convection and thermal radiation. First of all, let's discuss conduction. Conduction is transfer of heat energy by microscopic collisions of particles and movement of electrons within body. So it is a heat energy transfer which is transferred from one atom to another through collision. Suppose you have an iron rod and you bring it near fire. This end of the rod is, let's suppose, in contact with this fire. So these atoms will absorb heat energy, will basically transfer heat energy from this end to that end through collision of the atoms, and the energy will be transferred to this end. And suppose you are if this rod is in your hand, then you will basically feel the heat in your hand. So such a type of heat energy transfer is known as conduction. In case of conduction, vibrational amplitude of the atoms increase due to increase in temperature. Let's say in the example as I have given, when that metal rod or iron rod was brought near to fire, its temperature increased, so vibrational amplitude of the atoms of that rod increased, and so the energy was transferred due to increase in temperature. Let's take a system. Suppose this is a reservoir known as hot reservoir, which is maintained at a temperature TH, and suppose A is the area of this reservoir, and it is connected with this cold reservoir which is at temperature C. Now the heat energy transfer will take place from a hot reservoir towards a cold reservoir. But one thing should be kept in mind, that we are considering basically steady flow of heat from one reservoir to another reservoir. When this transfer takes place, we are basically interested in a quantity known as conduction rate. Conduction rate would be amount of heat energy transferred per unit time. In this case, this is equals to K times A hot reservoir minus cold reservoir over length. The separation between these two reservoirs is actually the length. In this equation, let me call this as equation A. You know the quantities. A is face area, TH is hot temperature reservoir, TC is cold temperature, L is the separation between these two reservoirs. K is thermal emissivity. K is the thermal emissivity. Its value depends upon the material of which this reservoir or slab is made. Depends upon the nature of material. In the book there is a table 18.6 on which emissivity values of different materials like lead, iron, brass, copper, white pine, window glass, etc. are given. You can easily see these values. Those materials in which heat conduction is at a higher rate are known as good thermal conductors, like metals, and those which do not have that high conduction rate are known as bad thermal conductors or insulators, like helium, hydrogen, etc. However, you are not always interested in good thermal conductors. Suppose if you want the can of a cola or your tea to be hot or cold, so you want the material of which the container is made up of to be a good insulator. There is a term, as you know, resistance in case of electrical systems. In case of thermodynamic system, there is thermal resistance. Thermal resistance is given by R equals to L per unit K, where L is thickness of slab and K is emissivity of the material of which the slab is made. So materials with higher value of R are good thermal insulators, while the materials with lesser value of R are good thermal insulator. And another thing you can see in this equation B is that resistance is inversely proportional to emissivity. As the emissivity of a material increases, its thermal resistance will decrease, and as the emissivity of the material decreases, its thermal resistance will increase. So R is higher means good thermal insulator, and lower value of R means good thermal conductor. Next related topic with conduction is conduction through composite slabs. Suppose in this case we have two composite slabs having the area same area. Let's say they have same area as A, but they have different thickness. Suppose this slab, that is a hot reservoir which is at TH temperature, has thickness L1 and emissivity K1, and this cold reservoir has thickness L2 and emissivity K2. Now as we are considering steady state, this means that the conduction from the hot reservoir to cold reservoir would be same. Conduction rate from the hot reservoir to the cold reservoir and from cold reservoir to the hot reservoir would remain same. And let's suppose that this Tx is the temperature at the interface. Now the conduction rate from this hot reservoir to this interface would be K1A TH minus Tx over L1, and conduction rate from this interface to this cold reservoir would be, since its emissivity is K2, area remains the same, this temperature is Tx minus this let's say cold reservoir is at Tc, cold reservoir temperature divided by its length, that is L2. Now due to steady state, this P conduction would remain same. This means that equation C and D could be equated. This means that K1A TH minus TX over L1 should be equals to K2A interface temperature minus cold reservoir temperature over thickness of slab 2. Let me call this as equation E. Now when you solve this equation E for the value of Tx, means you want to eliminate this Tx from this equation, the Tx comes out to be K1 times L2 times Tc plus K2 times L1 times TH over K1 L2 plus K2 L1. Now when you substitute this value into the equation E, when you substitute this value into equation E, the value of this Tx, conduction rate becomes equals to A times TH hot reservoir minus cold reservoir over L1 over K1 plus L2 over K2. In a more appropriate form, you can write this conduction rate as A times hot temperature reservoir minus cold temperature reservoir over, let's call this as summation L over K. This equation F could be considered as a generalized expression for more than two slabs, right? You have to calculate basically this thickness to emissivity ratio and sum them all, and you have to basically see the hot reservoir and cold, and the temperature of those composite slabs should be same, that is A. So this could serve as a conduction rate for composite slabs. Okay, let's do a numerical related with conduction. This is numerical 51 of Fundamentals of Physics book by Halliday, Resnick, Walker. It may change from version to version, but you can basically see the similar statement in your book. Consider this slab that was shown in figure. If I could show you, we are considering basically this slab, right? This slab, right? That length or thickness is 25 centimeter, is area of this slab is 90 centimeter square, and material is of copper. If high temperature reservoir is 325 degrees centigrade and cold temperature reservoir is at 10 degrees centigrade and steady state is reached, what is conduction rate? As we know that conduction rate is given by K times A hot minus cold reservoir divided by length. Now the length and area are given in centimeter. You can convert it into meters, and emissivity of copper is 401, and that length is thickness is 25 centimeter. When you convert it into meters, it would be 0.25, and area is 90 centimeters square. You have to convert it basically into meter squares, so you would divide it by 10,000, 100 into 100, it would become 0.01 meter squares. Now when you substitute all these values, the conduction rate would be, emissivity is 401, area is 0.01, hot temperature reservoir is 325 minus cold reservoir is at 10 degrees centigrade, and thickness is 0.25. This would come out to be 52 joule per second. In another numerical, which is numerical 54 of the version I have, you can match it with the similar statement in your book. The ceiling of a single family dwelling in a cold climate should have an R value of 30. Thermal resistance is given as 30. To give such insulation, how thick a layer of silver have to be? You have to find out this thickness, and we should know what is K for silver. From table I know that K for silver is 428. Now this R is equals to thickness over this K, and I can find this L by R into K, that is 30 into 428. This comes out to be 12,820, around that value. Now we move to our second heat transfer mechanism, that is convection. Convection is the transfer of heat from one place to another place by the movement of fluids like air, water, etc. You might have seen smoke coming out of the chimneys or from the puffing of cigarette. In this case, this basically is transferred through air. In this transfer mechanism, suppose a certain part of the fluid like air or water is in contact with some hot body, so the temperature of the fluid that is near to that hot body increases, and that basically fluid becomes less dense than the cooler fluids next to them. So in this case, through buoyancy, these fluid rise and they carry heat energy with them. Such a mechanism is known as convection. Convection is part of many natural processes. Atmospheric convection plays a fundamental role in determining global climate patterns and daily weather variation. Glider pilots and birds alike seek rising thermal that keep them aloft. Huge energy transfer takes place within the oceans by the same process. Finally, energy is transported to the surface of the sun from the nucleus furnace at its core by enormous cells of convection, in which hot gas rises to surface along the cell core and cooler gas around the core descends below the surface. So all these are different examples of convection. Third heat transfer mechanism that is I am going to talk about is thermal radiation. Thermal radiation, it is the emission of electromagnetic waves from all matter that has a temperature greater than absolute 0 Kelvin or minus 273 degrees centigrade is known as absolute 0. So thermal radiations are basically heat transfer mechanism through electromagnetic waves. These thermal radiations are not like ones used in electrical, like radio signals or X-rays, but suppose for thermal radiations of this kind, you are sitting near a fire and the heat energy that comes out of that fire to you and your body feels warm. This is because of absorbance of thermal radiations. No material medium is required for the transfer of thermal radiation. Let's say the thermal radiations from the sun reach the earth without any medium, they can travel through vacuum. The rate at which a body emits electromagnetic radiation is proportional to its surface area and its temperature, along with emissivity and sigma. More appropriately, I can write it down as sigma epsilon or epsilon A and temperature raised to power 4, where sigma is Stephen Boltzmann constant, and its value is 5.67 into 10 raised to power -8 Weber per meter square per Kelvin 4, and epsilon in this case is emissivity. Its value varies between 0 and 1, and if it is 1, it means that material is a black body radiator or a black body absorber. This emissivity equal to 1 means a perfect black body emitter, but such an ideal emitter does not exist. And one thing should be kept in mind, that this temperature should be in kelvins, right? And should be above 0 Kelvin, because 0 Kelvin is considered absolute zero. At absolute zero, no basically thermal radiation transfer takes place, means zero radiation at absolute zero temperature. Moving onward, we previously talked about the radiation emission rate as Stephen Boltzmann constant time emissivity times area into temperature in Kelvin, right? Let me call this as equation say G according to this lecture. Okay, now the body can absorb radiation as well from the environment. So the absorption rate of thermal radiation could be written in terms of the relationship Stephen Boltzmann constant sigma times emissivity times the area times the temperature of environment. So absorption rate depends upon this T of environment, right? Emissivity once again remains same. It should be between 0 and 1, and 1 in this case would means that a body is a perfect absorber, means it absorbs all the energy from the environment, right? Now if a body absorbs energy from the environment, at the same time it radiates energy into the environment. You can take the example of a human body. A human body can radiate as well as absorb heat energy. So we in this case we are interested in net rate of electromagnetic radiation, that is equals to absorption rate minus the radiation rate, or emission rate. So and putting the values from equation G and H into this, I would get sigma emissivity minus Stephen Boltzmann constants times emissivity times area times. You can write it down in this form as so this is our final expression for net radiation rate. Let me call this as equation I. So equation I depends upon the temperature difference between the environment and the body's temperature. This P net would be positive if net energy is being absorbed, and this P net is negative if net energy is being radiated or emitted. There are numerous examples of thermal radiation. One famous example is of a dead rattlesnake. A dead rattlesnake, let's say if a snake has died, rattlesnake has died, and it can basically bite a mouse or a hand that reaches around it within 30 minutes of its death. This is because due to radiation, thermal radiation. Pits between the eyes and nostrils of a rattlesnake acts as a sensor. So when a mouse or a hand comes near it, it quickly senses due to heat it receives from that mouse, and so it can bite that mouse after that. Okay, let's look into another numerical. A sphere of radius 0.5 meter, temperature at temperature 27 degrees centigrade and emissivity 0.85 is located in an environment of temperature 77 degrees centigrade. At what rate does the sphere emit? In part A we have to find emit, and in part B absorb thermal radiation, and what is the sphere's net rate of energy exchange. So first the temperature is given by 27 degrees centigrade. One has to compute it in terms of Kelvin. This would be equals to 300 Kelvin, and emissivity is given by 0.85, and temperature of the environment is given as 77 degrees centigrade. That should be equals to 350 Kelvin. Now using the equations G, H and I can find out the radiation rate, absorption rate and net radiation rate, right? And Stephen Boltzmann constant is sigma is given by 5.67 into 10 raised to power minus 8 Weber per meter square per Kelvin 4. Now using equation G, I can find out the radiation rate by sigma epsilon A and T4. Let me call this as now equation 1. One thing is missing, that is area of the sphere. Area can be computed by 4 pi r square, and the radius is given as 0.5 meter, right? Radius is given as 0.5 meter. You can use this, substitute this value and compute area, and then you can put the values of sigma, epsilon, emissivity, area and temperature of 300 Kelvin, and you will get radiation rate. Similarly, you can calculate basically the absorption rate as sigma, that remains same, emissivity remains same, area remains same, but however the temperature of the environment is given as 350 Kelvin. You have to calculate it and your result would give you the absorption rate. Now when you have computed basically equation 1 and 2, the value of absorption rate and conduction or radiation rate, then you can net radiation exchange rate can be calculated by P of absorption minus P of radiation. This would give you the net rate of exchange, right? If this comes out to be positive, then it means that particular body has absorbed more than heat than it has radiated, and if it comes out to be negative, it means the body has radiated more radiations as compared to its absorption. I am leaving the calculation of these values to you. You can easily compute those values with the help of a calculator, and you can see the result. So in this lecture I have basically given you an idea about different heat transfer mechanisms like conduction, convection and radiation, along with their formulas, and I have also tried to solve some numericals for you that may be helpful for you in practically solving numerical problems from the book. Hope you have enjoyed this lecture. I will be back soon with another lecture of applied thermodynamics. See you all. Thank you very much.